polynomials, we're going from n equals 0 to infinity, and they're going to be of the form Cn x to the n, and they're going to look something like C0 plus C1x plus C2x squared plus dot, 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 like that. And then a power series about A, and this is almost the difference between like, this is like what Maclaurin did, the first thing, and the second thing is what Taylor did, and he did it first, was n equals 0 to infinity. So in other words, the first one I just wrote is really a special case of this one right here, where it's basically shifted off. Like that, on out to n. In which the center A and the coefficients are there. So, that's basically what we're going to be looking at for these. So let's take a look at example 1. And so let's take a look at the geometric power series here. We've got n equals 0 to infinity of x to the n, and this is 1 plus x squared plus x to the third plus all the way out to x to the n plus whatever else. The center for this one, that offset I was talking about, is x equals 0. It's just right there. The coefficients are 1. The common ratio that's going on with them is x. And this converges to a over 1 minus r, that should be familiar to you, which is going to be 1 over 1 minus x if the absolute value of x is less than 1. And so basically what we find is that 1 over 1 minus x is going to equal 1 plus x squared plus x cubed plus so on and so forth. So we're, well, on the range, sorry, -1, x less than +1. This is what is called our interval of convergence. And hopefully in a few minutes, it'll make a little bit more sense. Interval of convergence. And the length of this here is actually called a radius, r. It's the radius of convergence. And here it equals 1, okay? Or r equals 1. Because if you think about it, it's going from -1 to 1, and so it's like halfway across that, like the radius is halfway across a circle. Now you might be wondering, why is this called a radius if it's just half of a straight line? The answer to that actually comes from complex mathematics, because when you extend this idea out into the complex plane, the actual convergence is inside of a circle rather than between 2 points for a line. So that's why it's technically called that. So if we look at this, we can do approximating polynomials. So what I mean by that is we can do P0 of x equals 1, P1 of x equals 1 plus x, P2 of x equals 1 plus x squared. We're just going out different distances along where we get there. And so the further out we go, the more accurately we're going to get the actual result for the function that it equals to there. And then I guess the fewer values you take out, the less accurate it is. So you have to go until it gets better. And you can see that in this picture. What you see are the different functions there. You see in blue, right here, you've got in blue, you have that actual function. And then you have the other functions and taking more and more terms for the approximation. And you notice that as you go further and further out, it starts to slant, and it really starts inside of here between the +1 and the -1. It'll really start to converge over and fit that. So in other words, this will start kind of curving up and start to hug the original function and start to match it more and more by taking more and more terms inside that radius of convergence. Okay? So let's take a look at example 2. Right here, we've got a center of x equals 2. And we can look at our first little, our first values as we do this here, -1/2, 1/4, so on and so forth. And then our ratio, -1/2 times x minus 2, which is going to give us this x minus 2 over 2, negative of it. And so basically this is going to converge if negative x minus 2 over 2 is less than 1. And so we get absolute value of x minus 2 over 2 is less than 1. And so we need -1 x minus 2 over 2 less than 1. And we add to -2 x minus 2, 2. And so right here, therefore, we end up finding our interval of convergence. And so the radius of convergence there is going to be r equals 2. Okay? And if we look down here, again, you can see that as we're going to higher and higher orders, more and more approximations, it starts to simplify to it. Feel free to go through and do those approximations, try some numbers in them, and actually see that as you take more and more terms, it's going to get closer to our actual thing here, which is 1 over 1 minus x minus 2 over 2. All right, that's what our sum is going to become. And so this is ultimately going to work out to be, I'm going to just skip that. You can do a little bit of algebra. It's going to turn out to be that. And so then that's what this is going to get closer and closer to as you take more and more terms. It's going to approximate closer and closer to that. Example 3, I will write out online for you. But basically, we're just going to use the ratio test there and then go through and look at what values for x will actually make it converge versus diverge. And I'm going to skip this one because it talks more about the interval of convergence and stuff. And I think this next part, I think if you see the next part first anyway, then this example would be a little easier. So cases of convergence, you can have it converge inside your range there and converge at the edges of it and then diverge outside of it. You can have it converge on just one side and diverge outside of it and at the other edge. You can have it go the opposite way and it can converge on the positive one and not the negative one. And then you can also have it just diverge on both endpoints and only converge inside the interval. And then finally, the last thing you can have is you can have it converge everywhere, or you can only have it converge right at A, where that's the only place that it actually gives you a good value. If you start to move away from it at all, it's not going to converge. So if you look at this here, it says the convergence of this series is described by one of the following 3 cases. And that's basically the cases I just told you. There is a radius of convergence, and it may or may not converge at the endpoints. That's the first one. It converges absolutely everywhere. All right, so that first one was the first 4. Sorry, that's these 4, basically those situations right there. That's number 1. It converges everywhere. That's 2. Or it only converges at there, and that's 3, at a single point, okay, at the center. So how do we test for convergence? Here we go. And this is what would make that previous example, I think, I think you might understand it a little more to do this. So how to test for convergence is we're going to use the ratio test, okay? or the root test, to find the largest open interval where it converges absolutely. And you'll see when you go back and do these, you'll see it done in that previous one when you take a look at it. So basically we're going to solve this, and the value R is called the radius. We already talked about it. Radius of convergence. And the interval of radius R, center at x equals a, is called the interval of convergence, which again, I already started talking about. So if R is finite, then you test for convergence or divergence at each endpoint. So if you actually have something, then you've got to go check it. Use a comparison test or integral test or whatever you need to do to see if the series converges at that value. If R is infinite, the series diverges for x minus a. I'm sorry, if R is finite, the series diverges for x minus a greater than R. It does not even converge conditionally because the end term does not approach 0 for values of x. All right, so it'll diverge outside of that pretty much no matter what you do. So let's try one of these, and you'll see what we're doing here. So ratio test. Okay, so we're going to do the absolute value. Now I'm going to ignore the -1 to the n minus 1 here because we're doing the absolute value. So that, just forget about it. So this is x squared times n plus 1 minus 1 over 2n plus 1 minus 1. And then we want to divide by the regular one. So I'm going to multiply by the reciprocal, 2n minus 1 over x to the 2n minus 1. This is going to equal x to the 2n plus 1 over 2n plus 1 times 2n minus 1 over x to the 2n minus 1. And so if you look, we have 2n plus 1, 2n minus 1. That means they have a difference of 2. So it's 2n plus 1 minus 2n minus 1, right? That's what it's going to be. What I'm talking about, it's going to be x to the 2n plus 1 minus 2n minus 1 kind of a thing. And so those are going to have a difference of 2 because, so if the top one is 7, then the bottom one's going to be 5, and it's going to have a difference of 2. So 2n minus 1 over 2n plus 1, that can be out there. It doesn't need to be inside the absolute value anymore. And then we have x squared absolute valued, but it's x squared. As we take this and take our limit out, this goes to 2 over 2 times x squared, because that's always going to be positive, which will ultimately just equal x squared. All right, so that got that. So what we now know is it converges absolutely if x squared is less than 1. And so we get that interval there. And if x equals 1, our summation becomes n equals 1 to infinity of -1 to the n minus 1 over 2n minus 1. And that will converge by AST, which you should be getting familiar with. If x equals -1, we're testing the inbounds now, or this both times at x1 and -1. Our sum is -1 to the n minus 1 times -1 to the 2n minus 1 over 2n minus 1. And that sum is -1 to the 3n minus 2 over 2n minus 1. And that'll converge by AST as well. And then our interval of convergence then, which we found, basically found the interval, we basically found it converges at both boundaries. So our interval of convergence is going to be from -1 less than or equal to x less than or equal to 1. And in this case, then that gives us r is equal to 1 as well. And it's going to diverge everywhere else. Okay? Anywhere else outside of that, it'll diverge. All right? So let's try and look at another one here. Here we've got the sum from n equals 0 to infinity of x to the n over n factorial. So let's do absolute value of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. And that's going to equal, we have the x to the n plus 1 over x to the n and the n factorials and stuff. You're going to end up getting essentially just 1 over n plus 1. Okay? And then that will go to 0, which is our value for rho, which is less than 1. And it's true then for every x. And so therefore, this converges absolutely for all x. There's no x's we have to worry about getting, or no equation or anything like that we have to worry about getting to be less than 1. So let's try another one. I'm hoping that lots of examples here will help, but let's take a look here. We have absolute value n plus 1 factorial times x to the n plus 1 over n factorial times x to the n. And you'll need to get good at dividing those factorials and exponents and stuff like that. So here, the n plus 1 factorial over n is just going to be n plus 1. And then x to the n plus 1 over x to the n is just x. And so this equals n plus 1 times the absolute value of x. And that goes to infinity for all x that don't equal 0. So therefore, this diverges everywhere except x equals 0. That's the only place it's not diverging. Okay. So last thing here, I believe the rest of this is just kind of giving you some ideas here. So operations on power series, like what can we do with these? Here, this is just telling us in this first one that we can multiply two series together as long as they are, you know, if they both converge absolutely on this radius, then we can multiply them together and get multiply them term by term together, I should say, and actually get a new series that converges absolutely in the same radius. So that's basically all it's telling us. We can go through and term by term multiply. The next one is a theorem that we can do term by term derivatives, essentially, if it's inside where it's converging. So inside that radius of convergence, you can go through and take derivatives of each term, and you will get new series that converge on the same intervals. So you can get new series there, and that works. It needs to be a two-sided derivative, just as a little extra added on there. And then here, we can also do the integration theorem, and that's basically telling us that, like with the derivative thing, if we're in an interval that it converges, we can actually do, we can actually integrate term by term as well to get an integral for it. So I know it's a lot of complicated looking stuff, but that's basically what it's telling us. And so let's do one to show you here what I'm talking about. This is actually in the book as well. In case you want to look at it again, I had it open here. Page 626, it starts at the bottom of 626 in case you want to look this back up. But basically what we have here is we're worried about our function here, f of x. And so it's going to equal over to this series, and it's going to do that. And so what we can do is we can use this to approximate some complicated function on this interval. And so what we're going to do is take the derivative of it, f prime of x. And so the derivative of x is 1. X cubed over 3 is x squared. X to the 5th over 5 is x to the 4th. And then so on and so forth. X to the 6th plus dot, dot, dot. So on and so forth, right? And this is going to be true inside the interval of convergence from -1 right there. And it's going to be, it's geometric with a equal to 1 and r equal to -x squared. All right? And so since it's geometric, we can get its value by doing 1 over here. So a is 1, 1 minus that -x squared. So you may need to look back at your geometric series if you don't remember that. So it's 1 plus x squared. And so that's f prime of x, which means we can then integrate that. We can integrate the f prime of x dx equals to the integral of dx over 1 plus x squared, which hopefully we've got now, we remember is the arctangent of x. And then all we really have to do is find c. To do that, you want to note that f of 0 equals 0, okay? Looking back up here, and right when you plug in 0 equals 0, therefore that implies, it's an implication, not a limit thing, that the arctangent of 0 plus c must equal 0, which means c must equal 0. All right, because that's what that is there. It's already a 0. Therefore, f of x is just going to equal our x minus x cubed over 3 plus x to the 5th over 5 minus dot, dot, dot. So that's our series. That series will actually equal the arctan of x, and it will be on this interval. Now, you can check, it actually does still hold for -1 and 1, but we're not going to do that here now. But it does actually still hold for those two as well. So we can put the or equals to signs there. Now, what you would find if you went in the next section, and I think it's a little simpler way to get to this, is you wouldn't start with the series, is you'd mostly start, when we do our next section, it will start with something like the arctangent of x, and then we will go through and do the Taylor series expansion of it, and it'll actually end up giving us that rather than doing it this way. I find that kind of method a lot better than this kind of backwards method of going through and taking a series and saying, hey, you know, what function does this series approximate? Usually, at least in my experience, it's always been a lot more advantageous to be able to find a series that approximates a function than try and say, hey, I have some function here, some geometric function. What series does it approximate? It's not very often that you come across a situation like that, but it could happen from time to time. All right, we have a couple extra minutes here, so I might go back up and actually do that one. What did I skip? I skipped, what did I skip? I skipped this one, example 3. So let's take a look at example 3, and hopefully now at this point it'll look a little better. So we're going to use the ratio test. So absolute value, again, ignoring ignoring that part right there. I'm not going to leave it crossed out, but the negative 1 to the n minus 1. X to the n plus 1 over n plus 1. And again, times the reciprocal, so n over x to the n. This is going to give us x to the n plus 1 over x to the n, and that's going to just give us the absolute value of x. And then the other thing we have is n over n plus 1. So we're canceling out all of the x's but 1. And so we'll end up with this. And that's going to take us out to, this is just 1 over 1. That's what the limit of that would be as n goes to infinity. So this will just leave us with the absolute value of x. Okay, and at that point, it's going to converge, right? That's the row. It's going to converge absolutely if the absolute value of x is less than 1. And it'll diverge, right? We were already talking about that. It's going to diverge outside of that if the absolute value of x is greater than 1. So really what we need to just check, so basically, you know, this tells us then that it's negative 1, x, like that, right? So we need to go in and check the edges. We need to check negative 1 and check 1. And so if x equals 1, our sum equals there is negative 1 to the n minus 1 times 1 over n, because x, or 1 to the n power, is just going to be 1. And if you look at this, this is alternating harmonic series, which converges conditionally. We've done that one already. And if x equals, oops, forgot to write x. If x equals negative 1, then we've got the sum of negative 1 to the n minus 1. This time, negative 1 to the n over n. So we have negative 1 to the n minus 1 and times negative 1 to the n. So that gives us our sum, and we get a negative 1 to the 2n minus 1 all over n. And 2n minus 1, if you think about it, whenever you multiply something by 2, you get an even number. And if you always subtract 1 away from it, it's always going to be odd. So 2n minus 1 is always odd. And so if it's always odd, 1 to an odd power is always just negative 1. A terrible summation sign. Is negative 1 over n. And that's a negative harmonic series which diverges. So our interval of convergence is negative 1, but not including negative 1. X less than or equal to 1, and our radius is 1. Okay, so that's pretty much it for a kind of quick through this one. And we'll take questions here in just a second.